Welcome back, everybody. So let's continue. I hope you will remember that lesson forever, that you should not ever write things like that. You should really make sure that either you use this notation with a random variable being equal to a specific value, which is an event, then you can use P, or a load too. But if you want to use just small x and small y, or a blue square, or 1 or 2, or actual values, you need the subscript to know exactly what you're doing. Because you see, EXY, it's a function defined on the Cartesian product. It takes x and y, so it's defined on the Cartesian product of the target set of big X and the target set of big Y. P of x vertical bar y is also a function defined on the Cartesian product of the target set of x and y, right? It also takes two values, x and y, but they don't do the same thing. They don't do the same thing, right? One of them computes the value that big X is small x and big Y is small y. The other one computes the value that big X is small x conditioned on big Y being small y. And again, I insist, big X, big Y, these are just functions from omega to a target set. These are random variables. They are neither random nor variables. Small x, small y, these are actual mathematical variable like a Java or a Python variable. You can replace them with anything. You can replace small x with 1. You can replace small y with a green square. That will work. It's just math. This is how math works. But big X, big Y, you cannot do that. These are not actual variables.
Sorry, can you quickly add me to the Zoom?
Oh, yes, absolutely. It was funny when we were in the lockdowns and everybody at home, and then the moderating TA was disconnected, and then I get a message via another TA who tells me the head TA is disconnected from the chat. But now we are fortunate enough that we are in the same room, so it makes it easier. Okay. So, okay, I've made my point. The difference between big and small. And by the way, this is only a convention. The fact that I'm using uppercase letters for the random variables and lowercase for the actual variables, it's only a convention, but it makes it easier to learn. Okay. So now let's go to information retrieval again. So do you remember this evaluation setup that I told you about when we try to evaluate whether a system is a good system or a bad system? The way it's done is that I take some collection of documents. Typically, it's going to be a collection specifically built for the evaluation. For example, a collection of aeronautics, I think, was quite popular at some point. So you have a collection of documents, and then you have a set of information needs that are also specifically designed for a specific evaluation benchmark. And then you ask people, lots of people, experts, non-experts, and so on. You give them a pair with a document and an information need, potentially a query that satisfies this information need. And that person is going to answer you, it is relevant or it is not relevant to me. It's a yes, no, yes, no, yes, no. It's relevant or it's not relevant. Imagine that now you do this 10 times, 100 times, 1,000 times, 1,000,000 times, 1,000,000,000 times, a quadrillion times, a heptillion times. Imagine that with our imagination, we can do so much, right? You know what thought experiments are with Schrödinger's cat. So nobody actually ever put a cat in a quantum superposition in that way, right? Fortunately, it's just a thought experiment. And what's cool with that, what we can do with our thoughts is amazing. So now I can just pretend that I'm going to do that heptillions of times. I will pretend that I have, you know, maybe I'm in the future with a population of heptillions of people, and I'm distributing documents and information needs to heptillions of people, and I'm just asking them, is that relevant or not? Can you imagine the value of a data set like that? Absolutely gigantic, right? So imagine that I do that. So that's just an example in practice of how it was done a few decades ago. So you see, the goal is to increase the documents. But now, I'm pretending that I have trillions of documents, millions of information needs, and heptillions of people to ask, of domain experts. So what does that mean? It means that I can even have since we are anyway in our thoughts, let's talk about science fiction. Imagine that I have the luxury to even use parallel worlds. So in every world, there is one person to whom I give a document, and I give an information need, and they tell me yes or no. And there are heptillions of worlds in which I do it like this. Omega is absolutely gigantic. And again, every one of these points here, every one of these points is some hypothetical world in which there is one person to whom I give a document, I give an information in, and it's yes, no. I insist in every world it's deterministic. If I give you a world, there will be one document, there will be one information need, there will be a yes, no answer. Heptillions of them, heptillions of them. Okay, so lots of queries, lots of documents, lots of domain experts. I changed a little thing in there for the purpose of experiments is that I'm not going to give them information needs, I'm going to give them queries. Right? And I'm asking them, with this query and that document, do you think that the document is relevant to the query? Okay. Okay, so you see the power of thought experiment is that I actually get to do that, right? What does that mean formally when I did that a heptillion times? It means that I have this absolutely super califragilistically enormous universe in which I can pick one world. And given one world, there is one query. In that case, that's the query information. Specifically pick that point. The query is information. What did I do? Well, this looks incredibly like a map from omega to something. What is a map from omega to something? That is a random variable. So I can define my random variable Q as in query, big uppercase Q because it's a random variable that associates every little omega to a query. All right, so Q is my random variable for the query. Now I have another random variable D, uppercase D, because it's a random variable, and that random variable for every one of these heptillions of worlds gives me one document. So this world right there, the document was the information retrieval book, right? So it's the same world. So the query is information and the book is information retrieval. And I have a third random variable that tells me whether the person that was in that world and looked at that book and at that query, turns out that the person said, yes, that query here, so sorry, that book here is actually relevant to the query information. Probably a lot of you would agree, right? This book information retrieval probably is relevant to information to some extent. So here, I get an answer. R is also a random variable, right? It's a random variable that maps every little omega to yes or no. So here, the target set is actually simple. It's just the set of Booleans, true, false. It's binary. So it's a yes, no thing. Okay. That's great because now I have my gigantic omega. I have three random variables, D, Q, and R. And now that I have random variables, I can start writing formulas with the random variables. So what kind of formula can I write? Well, for example, I could write the formula that I want the probability that R is 1, meaning that the probability that the person told me, yes, it's relevant, given that the document was this specific document, small d. Again, small d is a mathematical variable, so you can replace it with any specific book. So if I take a specific query, lowercase q, and a specific document, lowercase d, for example, this, then I can compute the probability that the person said it is relevant, given that the document was information retrieval, and given that the query was information. Who agrees that this makes sense? How do I do this? Well, imagine, again, you can do it visually. I have my heptillions of worlds. In these heptillions of worlds, I'm going to select the million worlds that have this book and this query, right? A million is nothing compared to heptillions, but in this heptillions world, in a million worlds, I have that book and that query. And in this million worlds, maybe I got 600,000 in which they said yes, and 400,000 in which they said no. So that the value of that formula will be in that case. How much? 60%, right? If hypothetically, I ask to 1 million people for that specific document D, for that specific query Q, is it relevant or not? And 600,000 of them told me yes, and 400,000 of them told me no, then the probability that R equals 1, conditioned on that query and that book, D and Q, that's 60%. Who agrees? Raise your hand if you agree. Okay, awesome. So this formula makes sense. It makes sense in my world with these heptillions of worlds. Okay. I insist, I know I'm repeating, I insist on the difference between the uppercase letters and the lowercase letters. The lowercase letters, D, Q, these are mathematical variables, and I can replace them with anything I want, with a specific book, a specific query. The uppercase TQR, these are random variables. Okay, and for one, I directly put a 1, right? I could also have put a small r, knowing that small r can be 0 or 1, but I can, again, this is a mathematical variable, so I can also put a 1 instead of the small r. Okay. So again, now I have a visual. Basically, if you assume that you only pick those words in which the document is small d, the query is small q, and then you compute the ratio. So this is the yellow and blue you eliminate. These are different queries and different documents. The blue zone is where you get exactly that query and document. And in that blue zone, you look at the proportion of r equals 1, r equals 0, and that gives you the value. Okay, this is just a diagram for a conditional probability. That's all it is. Note that it is a conditional probability with 2 conditions, right? That's the only thing that makes it different, but I can have as many conditions as I want on the right. Okay. Now, let's put again a hat of, I'm trying to build a system where there is a query that arrives and I need to return documents. Imagine that, again, this is our thought experiment. I have these heptilions people and I computed this for every D and for every Q. I have this. The value of that probably would cost trillions of dollars, right? But imagine I have that and I do have somewhere a file for every small d and small q, I have the value of that. How do you turn that into a useful information retrieval system if I give you the values of these? Does anybody have an idea? I give you small q and I ask you what small d should you return and in what order? Any idea? On Zoom? So I reformulate just to be clear. Imagine that magically I have access to some file on S3 or whatever on the internet that has a 2-dimensional table with documents on the rows and queries on the columns that gives me the value of that formula. So it's a huge matrix with D and Q, and I have all of these values. Now, if I have a specific query that arrives to my system, Q, that is basically a row in that huge matrix. So on that row, I have plenty of numbers. Every number corresponds to a document for that specific query. Which documents should I return? Yes, do we have the cube? Where is it? Yeah, go ahead.
I would return the one that maximizes the formula.
So the ones that
maximize the probability.
That maximize, exactly. Exactly. You want to maximize this. That's exactly the idea. I saw somebody wrote on Zoom, I will also come to this. But just to illustrate what you're saying is that you basically, let me show you this. You basically have the value, so Q is the same, right? Q is my query, but now I do it for D, for E, for F, for G, for all my documents. And I have a specific value for all the documents. And what you're suggesting is that we sort them, basically we maximize, so we sort them by descending value, and we return first the ones that have a very high value, right? So you agree that I would return F, and then D, and then G, and then E, right? Okay, so indeed, so if you did have these numbers magically, then you would have a search engine that actually ranks documents in a way that probably would be very good, because this is guaranteed to return the most relevant documents first. Let's go to Zoom now.
So someone posted the formula, the probability of, I'm assuming this is a, yes, typo, the document being D.
Oh, the mic is not on?
Is it not working?
I think it's connected normally.
Ah, yes.
Now it works.
The probability of the document being D depended on the rating R being 1 and the query being Q.
Yeah, the probability that the document is D, depending that is, yeah, you could also imagine doing something like that. That is a different approach. In fact, I'm trying to think, because this is thinking in real time. this is a different approach where you maximize this instead of the probability of 1. I think that might correspond more or less to what we'll see in 2 weeks in the language models, because this is basically language model Z, I would say, what you are saying here. This is also a very good idea, and again, in 2 weeks we'll come to it, right? But it's a different approach than the one that is on the slide. Yeah, so thank you very much. Again, that's an excellent suggestion as well. By the way, who sees that there is some ChatGPT taste to this? Some of you. In 2 weeks, maybe you realize why I'm saying that. That's very ChatGPT, the suggestion that your colleague did on Zoom. Okay. So let's come back to the slides. So I have these values. Now, ideally, either a document is relevant or it's not relevant, right, to you, then you would have basically just a 1-0 thing, right? So you have ones and zeros. That would be a Boolean retrieval kind of system, right? That says either or. But again, if you gave the same pair of document query to 1 million people in our thought experiment, you would actually get numbers like that. That might not be quite 0, not quite 1. Okay, so we rank, we sort like this. This is the idea that you suggested. And now we return those documents that maximize the probability of relevance, given that it's the document you're scoring and the query queue. Who agrees with that? That it's a good system? Okay. But there's a lot of assumptions here because I'm assuming I have these numbers, and having these numbers is much more difficult, right? So in practice, we don't have these numbers, but we can still, again, reason on that. But hypothetically, if I had them, then I could build an engine like this. Okay. Then you can extract from something like that some Boolean retrieval by basically picking those documents for which the probability of relevance, R equals 1, is larger than the probability of R equals 0, right? So for example, if I have a specific document on the left, a document D that looks like this, where I have a larger zone of R equals 1, then that would be a yes. And if I have a larger zone of R equals 0, that would be a no. But basically what we are saying is we're just saying if it's above 1/2, if the probability is above 1/2, then that's, I return it, and below 1/2, I don't return it, right? That would be a Boolean system. But if you take it as a score, then you even have a ranked system, right? So you could take the top 10 of that and return a mega Google search engine, right? Okay. All right. Now, this is less important. I'm just saying for completeness, it's also mentioned in the book. You can also do something a bit more, more involved by reasoning like this. What is the cost of a false positive or a false negative? Meaning, what is the cost if my system returns a non-relevant document, or if my system fails to return a relevant document? So you can assign weights like C0, C1, and based on these costs, you can estimate, it's similar to machine learning where you have this loss function, right? So you could estimate your loss or your costs of returning document D versus not returning it. So you can write this complex formula here, the cost of false positive, false negative, and then that gives you something. And in the special case that the weights are equal, C1 and C2 are the same, you just recover the case that we've seen before, right? Because you're sorting this. And again, this is based on sorting this probability of R equals 1 given a specific document and query. Okay. So we fall back to the previous methods because sorting by increasing this is the same as by decreasing this, right? I'm just removing the 1 minus 2 thing. Right? Okay, so this gives us the same method. That was just a parenthesis. Who is following? Okay. Because this is now going to get into the heavy math more and more. But this is why this is why I really wanted to take the time to talk about this thought experiment with these heptillions of people who gave us yes/no answers on specific documents and queries. That's basically our omega set. Before we proceed now to how we can try to estimate, because that's our goal now, we try to estimate this, right? But of course, we need to estimate it in a way that we can do without a heptillion people. We're going to make an assumption. in fact, we're going to make a lot of assumptions. Some assumptions might be reasonable. For some assumptions, you might think, okay, this is less reasonable, but then this is science, right? And you publish papers, you have a scientific discussion, and people can have opinions on whether or not an assumption makes sense, right? And if you think an assumption doesn't make sense, you can just do research, take another assumption and see what it leads to. But here is the first assumption that we can do. That's called the binary independence model assumption. So I'm assuming, I announced it at the beginning of the lecture, that we are relying on sets of words, not bags of words. Bags of words was for the vector space model. Here, I'm going back to the sets of words, the same one we had for Boolean queries. So all I know is whether or not a term is in a document. That's again a yes/no answer. So a document is a vector of Booleans. So it means that until now, I used small d and small q for the documents and the queries without specifying what that was, right? But in fact, if I come back to the idea that a document and a query is a vector, I can actually write down d as a vector, d1, d2, d3, and q as a vector, q1, q2, q3, right? Every row on my vector corresponds to a term, right? There's the first term, the second term, the third term. The order is arbitrary, maybe alphabetically sorted, or I don't know. I'm just using numbers here. So D1, D2, D3, and so on. So the size of that vector is just the number of terms, which we called M, big M at some point. And the query is the same. Now, if I have a bags of words model, I'm going to have positive real numbers. If I have a set of words models, I'm going to have zeros and ones, right? So every time I have this, it's a 0 or 1. So let's assume these are zeros and ones, not numbers. It actually makes things simpler. So it means that now I had my random variable big D. I can do it more fine-grained. Now I can define specific random variables, not for my entire document, but for whether or not a specific term is in a document. So for example, there is the random variable DETH that takes value in a Boolean set. It's either true or false. And that random variable tells me in that specific world, where there was a relevance estimate, is the term ETH appearing in my document or not appearing in my document, right? And so if it is appearing, that's going to be a 1. If it's not appearing, that's going to be a 0, right? So this small DETH over there, it's either a 1 or a 0, right? Either. I put the B Boolean notation to make it clear. So DETH is a 1 or a 0. This is the same. DETH is the same as D1, D2, D3. This is 1 or 0 in my vector, right? DETH. Maybe it's at position 4,372. I don't know. Uppercase DETH is a random variable that has the target set B, 1, 0. Okay. Now I can do the same with the query. So Q information, the small q information would be again this Q1, Q2, Q3. This is again a 1 or a 0. Maybe information is number 42 in that vector. And so Q information is either 0 or 1, the small q. And the uppercase Q information is again a random variable that takes Boolean values. Okay. So it means that in every world, DETH and Q information either take the value 1 or 0. Right? Okay. So now I'm going to take a few seconds to make sure that you agree that this makes sense. Let's take some value k. You notice that k is a small k. So small k is just a mathematical variable. It can be anything. So let's say it's information, for example. I could write d information equals d information. So k is just anything you want. dk, this dk is also small, the second one. Let me show you to be very precise. So k, you can replace with any word you want. Information, retrieval, ETH, whatever. dk, it's again a lowercase. So it means it's also a mathematical variable and it stands for 0 or 1, right? For example, you could have a specific document D. So D might be, I don't know. This is document D, this is small d. And what is d ETH, small d ETH here? Is it 0 or is it 1? That's 1, right? ETH is right there. So if this is small d and k is ETH, then dk is 1 in the case that D is that. So this is again a specific value here. I'm just not specifying it, but this is a specific value. This here is a random variable. This is the random variable where you're asking the question in the world in which I am, is the document containing the term K? Right. And now you can write things like, is my document containing or not, depending on what you put here, the term K, depending on the fact that it's relevant and that the query is Q, right? This, in fact, is also similar to what you wrote on Zoom before, right? So this is also kind of confirming that the formula you wrote on Zoom is actually making sense. The only difference with what you wrote is that I'm looking at a specific term here. I'm looking at a specific coordinate in there rather than at the full document. Okay. Who is following? Okay. So again, this formula can be understood in two ways. Either small d, small k is 1, and then I'm looking at the probability that the document contains term K, knowing that the query is Q and that it is relevant. And if dk is equal to 0, so if, for example, I would, what word is not in there? Algebra. So d algebra here is 0. So if d algebra is 0, so k is algebra, then the probability that the document does not contain term K, term algebra, knowing that the query is Q, ends that it is relevant, right? All I'm saying here is that this formula makes sense. This is what I'm saying. It's defined, it's well defined, and it gives you a real value between 0 and 1. Okay. Now I told you we are looking at this binary independent model, and I haven't told you yet what this means. My binary independent model tells me that when I look at the probability that the document is D, small d, I can actually assume that the terms ETH, information, retrieval, algebra, chair, whatever, they occur independently in the documents, independently. So I'm looking at all of these random variables, DETH, D information, D algebra, and so on and so on. They are independent. What does that mean for the probabilities? What do I do with them? Do I add them? What do I do? Independent. Yes? Yes, we can multiply the probability. It's magic. But again, I'm making an assumption here. It's not always true. It's only true because I assume independence. If I assume independence, then I can actually write this as a multiplication. So if I have a specific document small d, and I want to compute what's the probability that this is my document. This here is the document considering these Heptinian worlds. I'm just going to multiply on all the terms. For example, let's take terms ETH. What's the probability that big D ETH is equal to 1, because ETH is here, so small d ETH is equal to 1. So I'm looking at the probability that ETH is contained in the document and multiplied by the fact that the algebra is 0, because here algebra is not there. So I'm looking at the probability that algebra is not in the document. In other words, I'm going to put it in a different way. What I'm computing, if I want to know the probability that this is my document, I'm looking at the probability that it contains ETH times the probability it contains Zurich, times the probability it contains the department, times the probability it contains off, times the probability it contains computer, and so on. I could do it all the way with all the words that I find in there, multiplied with the probability that it does not contain the word mathematics, multiplied with the fact that it does not contain the word algebra, and I can go on with the entire dictionary of that is the complement of that, right? So this is essentially what I'm doing here. The probability that this is my document is the product over all the words that are in there, that they are in the document, multiplied by the probabilities of all the terms that are not in there, that they are not in the document. This is the binary independence model. Yes? Yes, it's again part of my thought experiments. Let me re-explain that with the thought experiment. Because this, what I'm writing here, is actually only some ingredients in the complex calculations that we are about to do, right? What we want to do really, again, let's come back to where did I put it over there? what is our top goal? What we want to do is we want to calculate that. In a simple, this is our goal. In order to calculate that, this is parameterized. There are two parameters in there. It's small d and small q. Whatever my small d and my small q, I want to calculate that. What is d? This is an example of what d is. Another example of what d is this. And it can be any book in the ETH library. It can be any web page. So I need to evaluate that for every d. Now I'm going to be rewriting this formula in plenty of ways. And when I do write this formula, I'm going to have somewhere in there, I'm going to see probabilities that big D equals small d for a specific value of d. So the only thing that I'm doing here is that I'm saying, whenever in the course of our computations trying to estimate this thing, we actually see somewhere the probability that we have a specific document, it's going to appear as a factor somewhere. I want to know how I calculate this. How do I estimate the probability of this? Visually, if you consider that third experiment with the heptillions of worlds, this is specifically referring to how many worlds have this document, maybe 1 million of them, right? So then if I had the view of all the worlds, I would do 1 million divided by a heptillion, right? But this is just machinery. It's only mathematical machinery to compute things. So I need to do this here for every small d. This is only an example. And I would do the same for every book in the library. And so what I'm saying is that if I have a specific book in the library, how do I compute this? I compute it as a product, and the product is taken over the terms. This is my product. It is if you look at these heptillion worlds. Because in the heptillion worlds, maybe there will be 1 million of worlds with this. There will be 1 million of worlds with a book on butterflies, and so on, right? So it might be that if I take a book that is about butterflies, then it doesn't contain the term ETH. So you see, it's not everywhere 1. It's going to be 1 in some places. It's going to be 0 in some other places, right? And so this is just a mathematical thing, is that if I want to know the probability that this here is the document, that this is the document I'm looking at, then I need to look at, does it contain this? Does it contain this? Does it contain this? Does it contain this? These are all positive indicators. So you just multiply the probability that all of these worlds are contained. And then you then need to deal with the worlds that are not in there. And the worlds that are not in there, then that would be 0. The small decay would be 0. And then you multiply on the rest of the dictionary that it doesn't have that. So when this is an approximation, this formula. What you are actually doing is you're computing the probability that the document contains exactly those worlds, but not necessarily in the same order. This is why it's an approximation. It might not be the same cardinality, it might not be the same order, but you're just, with this multiplication here, computing the probability that it contains all of these worlds and that it does not contain everything else. If that's the case, that it contains all of this and it does not contain the rest, there's a very good chance this is that document. But it's only an approximation, and this is why we said we are assuming that the terms occur independently, right? So then we can write this formula in this way. Okay? Does it help? I told you it's heavy math, right? It's a bit more heavy. But this is more like a mathematical tool that I will need in my calculations, right? So the probability that I have a specific document, you can actually estimate it based on the terms, right? Okay. So this was my assumption. I'm assuming that if somewhere along the way that we're trying to compute this thing, we ever see probability of big D equals small d, if we ever see that, then we are authorized to replace it with the multiplication here because we assume that the terms occur independently. So now let's go back here. We want to build an engine based on these values, and we are going to try to estimate that value, right? So a starting point could be the base formula, right? So let me start. Let's forget about the query right now. Let's just do it with this. So if we were to compute the probability that document D is relevant, not knowing the query, we could rewrite this with base formula with the probability that the document is D, knowing that it's relevant, times the probability that it's relevant divided by the probability that it's document D. This is just the base formula, right? It's the same thing I did with the umbrella in the rain, right? And now, to explain also why you might be surprised, like what does it even mean to write the probability that the document is D? But it's exactly the same that when I was asking what's the probability that it rains, that's not making any sense, right? Either it rains or it's not raining, like you watch, it's not raining. So what does it even mean that it's the probability that it rains? Well, the probability that it rains was just some artificial thing to compute stuff, right? I just wanted to compute a subjective thing in there. So again, what's going on is that I want to estimate the probability of relevance to build my system. I'm going to use the trick that we saw with the umbrella in the rain, hoping that it works, by swapping the two sides, saying I want to compute the probability that it's document D given that it's relevant. And of course, I have all of my base formula factors in there. But remember, the magic of the base formula is just that it swaps sides. And what I will show you is that it's much easier to compute the probability of D given D knowing that R equals 1 than it is to compute the probability that R equals 1 given that D is D, right? I'm just cheating by swapping the sides. But again, the meaning of the formula P D equals D knowing that R equals 1, it only makes sense in our thoughts with this thought experiment with the heptadians of worlds and our omega. The meaning of that in reality is not necessarily clear. It only needs to make sense mathematically for our formulas to be correct. And I will add, before I proceed, one thing, is that this is debated. There are people who doubt these things, who basically are very critical of the Bayesian approach, and who say, no, you cannot do things like that. So this is an entire school of thought, the Bayesian approach, and you can have a debate on that, whether it actually makes sense. But mathematically, it is formally making sense. That is for sure. All right. So now, this is the base formula. You agree that I can add now Q in the condition, right? It's still true. You can also write the base formula adding everywhere an additional condition, right? Who agrees that you can do that? I'm only additionally conditioning on Q, right? But I do it everywhere. It's like a renormalization factor. Okay. Now, note that what I have on the left is now exactly what I want to estimate. And what we will see, and we'll continue next week, is that it's much easier to estimate what is on the right than to estimate what is on the left, right? So in fact, there is a series of tricks that we are going to use to simplify and simplify and simplify the formula on the right. And the first trick, because I still have time to show you that, is that this is the formula that I told you using the base formula. I'm going to write exactly the same formula, but now with R equals 0. I can do that, right? It's also true. And now I'm going to divide. I'm going to compute the odds that it's relevant. Remember that the odds is the ratio between the probability and the probability of the complement. So the odds that R is 1, that's basically the probability that R is 1 divided by the probability that R is not 1, meaning 0, with the same condition. So I'm going to divide. And if I do the division, this divided by that, look what's happening. Do you see that the denominator is going away? You're basically dividing. So if you want to compute the odds that it's relevant, you divide this divided by that. So you divide this by that. And do you see we already got rid of the denominator because you basically have this both on the top and on the bottom of the division. Who agrees? Right? So we are basically dividing this by this, and this is what I wrote here. So you see, in only one slide, I already got rid of 1/3 of this scary formula. The denominator is out. And the only observation that I'm making here is that remember that what we want to do is to sort by the probability of relevance. Who agrees that sorting by the probability of relevance is the same that sorted by the odds of relevance? It's a monotonous function. It's P over 1 minus P. So if you sort by P or if you sort by P over 1 minus P, it's the same thing. So this is how I already managed to get rid of 1/3 of my scary formula, right? This goes away. And this is where I am now. And I can even continue, right? I can do this. What do I have on the right? This is again an odd. It's the odd of relevance given query Q, right? So I can rewrite it in that way, right? So what will come next, and that I will do next week, we are just going to do some cooking with these scary formulas. I'm just going to take you through finding tricks to rewrite and rewrite and rewrite and rewrite. And at the end, we'll just come up with something we can actually compute. It's magical. And then instead of having my heptillions of worlds of things that are totally impossible to do in practice, with the magic of the base formula, I'm actually able to compute things that involve probability that document is D and so on, which is not clear why it makes sense or not. We don't care. This is just math. We just put our mathematician's hat for a moment and then arrive with a result at the end that gives us the ranking, right? So I hope it addresses also the question that you raised when I said, okay, the probability that it's a specific document. But again, there are many scientists who doubt that Bayesian is the way to go. And this is a perfectly fair argument to ask. Okay, so I told you it's heavy math. It's a bit more complicated, but I'm trying to really explain it step by step. And next week, I'm just going to continue to modify this formula in order to arrive at the end to something interesting, right? So this is almost a cooking show that I'm doing here, where I'm just cooking mathematical formulas here. Okay, who got scared? Totally fine. This is a more complicated lecture, right? But we'll take it from there next week and just continue. And at the end, we're going to have a system. And there will be a surprise. The formula we will get at the end will be a surprise. So, okay. I think that's it, right? We have enough for today. So I hope you enjoy your meal. I hope you enjoy the exercises with the TA team. And the exercises on that, don't worry, for the exam and so on, it will be not too complicated, right, at the exam for these last 2 weeks. So don't worry too much about it. And also the exercises will be natural enough. It's actually both going to be fun and at the same time, not too scary. All right, thank you very much, everybody. See you next week at 10 a.m. And then I will continue to do some mathematical cooking. Bye, everybody.